Okay, so we're to 5.1, systems of equations. Now a system of equations, you can see that we have two equations listed here. 3x minus y equals 7, that's one equation, and the other equation is x minus 2y equals 4. This brace here says that we're going to work with those two equations together. That's why it's called a system of equations. Now you can have bigger systems, but for our purposes in chapter 5, we're just going to have two equations with two variables. Each equation is in terms of x and y. Now we've been working on graphing those linear equations in two variables. That's what we were doing in chapter 4. So now we're going to work with two of them at once. Okay. So in order for a system of equations to have a solution, the solution has to work for both equations. All right, and we'll see what this means later on when we get to the graphing part. But first they want to know, they give us an ordered pair and they say, is the ordered pair 2, -1 a solution to that system? So what you're going to do is you're going to take the top equation, put in 2 for x, and put in -1 for y, and you're going to see if that's true or not. So here we're going to get 6 plus 1, does that equal 7? Yes, but that's not enough. That doesn't make it a solution. We have to check it in the other equation as well. So same point, 2, -1, this is our x, this is our y, but we're going to plug it in the bottom equation this time. So we have x minus 2y equals 4. That's the equation. And we're going to put in 2 for x and -1 for y. And if that equals 4, then that'll tell us something. So we get 2, it's going to be plus 2, which equals 4. So both of those statements are true. This one's true. And this one's true. That means that the point that we had, 2, -1, is true for both equations. Therefore, it is a solution. So yes, says is 2, -1 a solution to the system? Yes, because it works for both equations. Now they ask us, is 3, 2 a solution to the system? Well, we're going to do the same thing. We're going to use this time x is 3 and y is 2. So take the first equation, 3x minus y equals 7. And we're going to put in 3 for x and 2 for y. And we'll see if we get a true statement. We get 9 minus 2. Does that equal 7? Yes. So it works for that one. Or I guess I should say true like we did on the other ones. Let me erase that. All right. So true statement there. And now we're going to take that point, but we've got to use the other equation. The other equation is x minus 2y equals 4. And we're plugging in 3 for x and 2 for y. Now this time we're getting 3 minus 4. Does that equal 4? No, that's false. So the point 3, 2, it worked for the first equation, but it doesn't work for the second equation. Therefore, it is not a solution to the system. So not a solution. Has to work for both of them. And it doesn't. It only works for the one equation. All right. Now we're going to show you how to solve a system of equations. So we do, and there's several methods, but the method that we're going to work on today is the graphing method. So we've been working with some graphing before. So what we're going to do is we're going to graph this first equation. We can call it equation 1, I guess. And how are we going to graph that? Well, there's a couple ways we could do that. We could make a table of values, or we could use the slope and the intercept. We'd have to put it in slope-intercept form. But let's go ahead and just make a table of values here. Sorry about that. I wish I didn't do that. Oh, man. Goodness sakes. All right. So let's say we put in 1 for, or let's use the intercepts. Let's put in 0 for x, 0 for y, and then we'll have to pick another point. We'll do that in a minute. Okay, if I pick 0 for x, I get this statement. So I get negative 3y equals negative 3. Or if I divide by negative 3, I get y equals 1. So that's one ordered pair that I have for the first equation. Now let's say I plug in 0 for y. So x minus 3 times 0 equals negative 3. And then that's going to give us x equals negative 3. All right. Now I'm just going to graph those 2 points. We have 0, 1, which is right there. And then we have negative 3, 0, right there. And we can draw that line. Might be better if we had more points. We normally like to have 3 points, but I'm going to run out of room on this problem. Okay, now I need to do, I'm going to switch colors, go to blue. I'm going to do equation 2. So that gives me x plus y equals 5. If I make a table of values, x and y, if I pick 0 for x, I get 5 for y. And if I pick 5 for x, I get 0 for y. So we just want two numbers that are going to add up to be 5 for that equation. So I can graph those, 0, 1, 2, 3, 4, 5. And 5, 1, 2, 3, 4, 5, 0. And I get a line. A ruler really helps on these right there. Now, it looks like I have a point of intersection. That point of intersection is going to be the solution. Let me go back to, let's use green. This point right here is going to be the one point, in this case, that makes both the top equation true and the bottom equation true. Now, it looks like that point is going to be 3, 2. Now, sometimes it's hard to do these by graphing because our lines get off a little bit. I put it in set notation. A lot of times we will put it in set notation. But that would be the solution, that ordered pair. And you can check it out and see if it worked. If you put in the bottom equation, 3 plus 2 equals 5, so that's not a problem. And in the top equation, you'd have 3 minus 6, which is negative 3. So yeah, that's the solution. All right. So the point here when we're graphing these is we try to graph each equation individually, and then we see if they intersect. If they intersect, that point of intersection, that's the point that satisfies both equations, and that makes it a solution to the system. All right. That's our goal here. So now we have another one. The top equation is in slope-intercept form. So let's call this equation 1. I'm just numbering so we can keep them straight. In equation 1, we have a slope that's 2 and a y-intercept that's also the point 0, 2. Now when we're graphing, we're going to graph using the slope and the intercept. We graph the intercept first, 0, 2, which is right there. And then we're going to count up the slope, rise over run. We can make it 2 over 1. We're going to rise 2 and run 1. Rise 2 and 1. And we get these ordered pairs. Get a line like that. And that's how we graph it using the slope and the y-intercept. All right. Now we're going to do equation 2. Let's call it equation 2. And it didn't change colors on equation 2. And now that one has a slope of negative 1 and a y-intercept of 0, negative 4. Remember, it's going to cross the y-axis at that point. That's why it's called the y-intercept. So 0, negative 4 is down here. 1, 2, 3, 4. Right there. And our slope is negative 1. Now, when we're counting our rise and our run, then we have to go negative in one direction, but not both. So down 1 and to the right 1. Oh, that's a problem. Erase that line. Okay, so down 1 and to the right 1. Down 1 to the right 1. And we're going to get this, or you can go up 1 and back 1. Up 1. Now, can you see the point of intersection? Well, my lines aren't perfect. Ruler would help. Having a flat surface to write on would help. But we'll look for where they cross, and we'll just take our best guess there. It looks like it's about -2, -2. So I'm going to say it's that. I won't put it in the set notation this time. I don't think your book's going to do that. I think they're just going to write the ordered pair. Now, you could plug those in, see if they work. Let's see, for the top equation, you get -4 plus 2. Did I do this? Oh, because I wrote it wrong. It's -2, -2. So there, that looks a little better. It works for the top equation if you plug it in, and the bottom equation, it's going to work there as well. So there's a little bit of inaccuracy when we're graphing these. We just do our best, and that's about all we can do. All right. So for the next one, we're going to graph that first line. I could think of ordered pairs, or if I wanted to, I could write it in slope intercept form. Let's see, which way do I want to do it? Well, if I take that top equation, it says -x plus y equals 1, and I rewrite that as y equals x plus 1. So I could put that x on the other side. I could do that. Then I would know the slope. Slope is 1. And the intercept, the y-intercept, is also 1. So it's going through the point 0, 1. All right. 0, 1. Right there. And then my slope is up 1 and over 1. And so I get a good line going through like that. That would be the first one. Now I'll do something similar with the second equation. So here's my second equation. It says 2x plus y equals 10. So if I rewrite that, I get y equals -2x. Put the 2x on the other side, plus 10. My slope is -2. And my y-intercept is 0, 10. That's going to be way up at the top, 0, 10, right there. And my slope is -2. Again, you're going to want to make that -2 over 1 so you can do the rise and the run. Down 2 and over 1, down 2 and over 1, down 2 and over 1. Sometimes you get lucky and you land on the line, so that's always nice. Well, that's not a very straight line. All right, well, oh, man. It's still not straight. Okay, let's see what that point looks like about. All right, it's going to be about there. I'm going to say that point is 1, 2, 3, 1, 2, 3, 3, 4. Now you might say, well, you know, the line's not very straight, or that point doesn't work. Yeah, it's going to be pretty close, though. You could plug them in and see if they actually work. That point actually does work if you check it. But it's okay when we're doing the graphing method. Sometimes there's going to be a little bit of inaccuracy. Don't worry too much about that. Just do your best in graphing the lines, and then finding that point of intersection, just do your best. We have other methods for solving these systems of equations, but graphing is a good method to start with. All right, we have another problem, but I think I'm going to have to wait. So I'm going to close this video out, and we'll pick it up in the next video. It's going to time me out.